Good afternoon. My name is Stefano Terna. I'm a physicist and I work as a data scientist and an Internet of Things architect. This afternoon I will talk to you about how we can combine together machine learning and Internet of Things techniques in order to extract very useful information from lifelines. We live in an era in which new technological opportunities continuously push forward the possibility we have to convert normal things into smart things. And we have heard in the previous talk about intelligent quality. Now we are trying to convert a standard standard lifeline, into an intelligent lifeline. Okay, so in fact, what kind of challenges can Lifeline present to us nowadays? After all, we know almost anything about them, we know how to build them, we know how to install them, we know how to make them secure, and we have very precise procedures on how workers should use them. Indeed, some issues arises about lifelines if we start looking at them under these particular perspectives, namely under the presence detection perspective and under a maintenance frequency perspective. And let's see why in much more detail. So from a presence detection point of view, we have to firstly keep in mind that workers on fault protection lifeline usually operates on unsupervised areas. And moreover, if we think at a big area with a lot of buildings inside, usually the worker presence is recorded just at the entrance during the accrediting procedure, while little or no track is given of the actual position of the worker within the area once he has entered. Under this condition, in case of an accident, the lack of knowledge about presence and location of the worker may delay the execution of the expected contingency plan. And this is the first issue we can identify correlating presence detection and lifelines. On the other hand, passing to the maintenance frequency issue, well, we know that for protection lifelines must require regular maintenance to preserve safety. But different amount of usage of a lifeline will exhibit different degree of wear of consumption of the lifeline. So a lifeline used for let's say 10 hours per month will exhibit a different degree of wear than a lifeline used for let's say every working day of the month. And again, the lack of real-time knowledge about the actual usage and load of the lifeline forces the maintenance intervention to be planned mostly based on, say, repetitive and non-optimal regulations. As a result, maintenance activities, maintenance actions can be taken either too early, which turns out to be economically non-optimal, or even worse, too late, which is safety non-optimal. Keep in mind that we are speaking about people's safety. Maintenance is not a matter of setting a reminder on Google Calendar just to remind us when the next maintenance intervention has to be done, but it is more a matter of the awareness we can gain from how much the lifeline is used to when and how I have to perform the maintenance. So it turns out that an automatic presence detection system would very well help us in addressing both issues. Evidently, the presence detection issues, if we build a presence detection system, is goes by itself. And if we add to the presence detection system the ability to detect the start and end times of each intervention, of each worker intervention on the lifeline, we can in some way measure the real, the actual usage and load of the lifeline, so addressing also the second part of the issue, which is the maintenance frequency prediction. If we look around, current attempts to track worker presence rely nowadays on worker voluntary actions. So if the worker does not comply with the required policies, we are missing the information. I mean, if we require him to use a badge with a badge reader, or if we provide him with an app on his smartphone and he has to tap on the application, or as it is the most frequent case, if we ask him to sign a logbook, then maybe this cannot be performed, or maybe the logbook gets lost, and so on. So for the requirements, we asked ourselves for the system. The first one, the system should be automatic. So presence of the man on the lifeline, something that tells us there is a man on the lifeline, without requiring the man to perform any kind of extra operation more than the usual ones. Second requirement, non-invasive. So it is required for our system to not compromise the mechanical properties of the lifeline with all the certifications that go with the mechanical properties. And it is also required, it should also not require very complex installation procedure. The third requirement is the adaptive requirement. We want to target very different operating conditions, so not only roofings, which are the most frequent example that can come to mind, but also, let's say, bridge cranes or electric turbine water pipelines. Never remember how to tell it in English. So here is our idea. The shuttle, or the carabiner, to which the worker is attached, generates high-frequency vibrations on the lifeline. And these vibrations propagate along the lifeline itself, and we capture them with an accelerometer, this one, because in the picture it's not very clear, this one. We capture them on one end of the lifeline. But at this stage of the solution, we does not know almost anything, because together with the information hidden, the information of the worker presence hidden within the acceleration that we collect, there are a lot of other data that we are collecting. And here is where machine learning and the Internet of Things come to help us. Let me just introduce these two technologies with some definition. Supervised machine learning is, we can define it as a set of algorithms which learn by examples how to extract useful information from raw data. So let's think at raw data as the acceleration data that we collect with the accelerometer, and let's think at the useful information as the worker presence that we need. Just to make a little example, these sort of algorithms, if you've never heard about them, try to simulate how our brain works. This morning in the beautiful talk about visual enhancement system, we were given some introduction on the fact that our brain is able to generalize from examples to classify new things that we have never seen but that are similar to the examples. Well, supervised machine learning algorithms behaves exactly in this way. On the other side of the slide, you see Internet of Things, which is a more technological stack of technologies which enable us to communicate, remotely communicate with normal, let's say, everyday legacy things. And what we can think of a lifeline other than some legacy thing. And so, coupling together, combining together these two technologies, we try to convert a lifeline in an intelligent communicating, we call it smart lifeline. Let's see how it works at a higher level. I will usually, sorry, a parenthesis, usually it takes me more than 25 minutes to cover this topic. I will skip the more technical details, and maybe we can come back to them if you like, and if there is time for questions. So we have the lifeline, we have the vibrations generated by the carabiner, and we couple the accelerometer to the lifeline. You can see an example of the raw data acquired along the z-axis. An accelerometer can measure the acceleration along the three directions, three-dimensional. And just to give you some more technical information, it acquires measures at 800 times per second. The accelerometer is wired to an intelligent unit which is installed near the lifeline, and it is powered by a solar panel. So the accelerometer captures the data, the intelligent unit collects the data. We install a neural network, which is the machine learning algorithm we choose inside the intelligent board, and we will come back to it in a minute. The acceleration comes in, and if there is, the worker presence comes out on the other end. What is worth mentioning here is that, well, first we have chosen the machine learning algorithm. Neural networks, we have chosen them because the behavior they manifest with respect to generalizing previously seen example to previously not seen new cases. The second thing that is worth mentioning here is that worker presence is detected completely on the lifeline. At this stage of the solution, there is no connection, there is no internet connection with anything. All the system can complete its work to detect the worker presence just staying on the roof or wherever. But at some point in the story, internet comes in, and it is when the intelligent unit detects the presence, it pushes it to remotely operating support desks by means of an Internet of Things cloud platform. You can look at the orange cloud as a platform that enables the communication with remotely installed devices. Once the data are available to the remote operators, this is just an example of the user interface, they can keep track of when and where the worker is operating, and they can keep track of how of the duration of the worker intervention. And the system in the background, summing up all the durations of all the workers, can compute a metric of the actual usage and load of the system, and so we can make predictions on maintenance frequency. But I have kept to you somehow hidden the magic that is going on behind the scene here. So some data comes in, and a very precise information comes out. How does it work? Well, as I was saying to you before, these algorithms works learning by example. So we have to feed to them a huge amount of examples. A huge amount of examples of what is the yes case and what is the no case. So what is worker presence and what is no worker presence. So we need, and we will look in a second, some process to gather what we call annotated data. So the raw data with a label which says this raw data is an example of a useful information. Then we pass this annotated data through a training platform which performs, if you like, we can go through the details of this stuff, mathematical stuff, but maybe it is not the case here. No. The training platform does what its name says, so it trains the algorithm. What it comes out is a trained algorithm able to distinguish the cases. And after the algorithm has been trained, we can upload it remotely over the air on our already remotely installed intelligent unit, so that we are able to alter the behavior of the intelligent unit already, even if it is already been installed. Let's say that a new phenomena start occurring near the lifeline, and we have to clean it from our data. We just make a batch remote new training, and the intelligent units start detecting in the correct with the correct behavior. And this is also how we can achieve the adaptive requirement, because we can train different models for the different environmental situations. Just some insights about the training process. So now we concentrate on this case, the roofing case. We built a training laboratory with these characteristics, 140 meters of lifeline, 28 supports, 13 curves to simulate a very complicated scenario. Then we installed the intelligent unit on one end of the cable, actually also on the other end, but just to let you. Then we started doing stuff as worker on the lifeline, walking, stopping, hitting against the intermediate supports, crossing curves, and so on. And we, with the help of a mobile application, we labeled the data. This is an example of acceleration, and the spikes are real worker activities along the lifeline. And this is the same data with the labels on them. So you can see that, for example, here is a case of walking at 100 meters distance from the accelerometer, just to give you some insights on the detecting capacities of the system. To recap, this is the data set we built. We made trials on concrete and on metal because they exhibit very different behaviors with respect to vibrations. And for each of these cases, we collected walking, support hitting, corner traversal trials. Silence is easy because you just leave it there to record. And then we collected outside factors such as rain, wind, and thermal expansion in the early morning and late afternoon. Because thermal expansion generates along the lifeline vibrations which in a first stage are very similar to the vibrations generated by the carabiner moving very far from the accelerometer. I said to you before that the accelerometer captures the data 800 times per second. Each unit of this test has a duration of average 10 seconds, 20 seconds. So you can imagine that each one of this number is 10,000, 20,000 measures. And so this is the reason of the huge data set we collect. So, I'm toward the end of the presentation at the first higher level, then we have time for some more technical details. Just to recap, we spoke about the Internet of Things edge design and the machine learning model, the neural network. For edge design, we intend that we want the system to be installed in close proximity of to the lifeline, so we do not have wired connectivity. We have strict power consumption constraint because we want the system to work continuously, also without solar panel for a certain number of days. We skip this. These hardware constraints put on us constraints on how we can design the algorithm to fit within the hardware we can install over there. And so we built not only the neural network model, but also a pre-processing, which, let's say, compresses the data, passing from 3 dimensions, 800 times per second, to 170 feature values per second. This is quite important because we can both achieve 2 targets with this. First, we can make the neural network working within the constrained hardware. Second, we can move this data from a remotely installed unit to the central training server, so that we can make new training in new situations. And just skip all the technical details here. And here. Okay, so these are the conclusions. We were more conservative on the false positive side, so that we don't want the system to give a presence when it is not. And we gain a very important result of less than 1% false positive detection. False negative detection is less important because you have to look at this as each case, and in this situation is 1 second case, so a man just doesn't work for just 1 second, it works for 10 to 5-10 seconds, so we just count these data coming out from the algorithm, and we obtain a detection precision of 100%. So, to recap, to conclude, are lifeline challenging? At least in my opinion, yes they are. If you are interested in looking a real installation of this, you can come and join us at Genesi Italia booth in Hall 6. And thank you.
Thank you very much, Mr. Terna. I think this is really innovation that you showed us today. And so, are there any questions regarding this, let's say, new technique or innovative technique? Please use the microphone.
I would like to know how the neural networks in the clouded environment and the intelligent monitoring are connected to the reduction of the number of injuries and fatalities for workers on the roofs.
Okay. I have to skip back. Okay. Maybe we are. It is not a matter of reducing the injuries, it's a matter of most tempestive intervention in case of an injury, because we know where the worker is and when it has started working and it has stopped working first. And second, it is a matter of maintenance. So we can predict more accurate per installation basis maintenance. And this can affect worker injuries, because if the lifeline is not properly maintained, the lifeline does not simply work. Don't know if I have answered you.
Well, not exactly. I think that you are using an extremely sophisticated apparatus and extremely expensive methods, while the problem in the field is really of a different nature. We have workers who are poorly trained and not necessarily in the cloud computing and intelligent machines. They simply don't know what's the breaking strength of the rope.
Yes.
Aren't we going a little bit too far into a too expensive way, while problems can be solved for much less money?
No, it's not a matter of expensiveness, since what I was citing at the beginning, enabling technologies allows us today to build such kind of solutions with very few efforts. But I agree with you with the fact that workers on lifelines are not at all trained to such kind of system, but they are not required to be anyway, because these kind of technologies just work on behalf of us. I mean, the worker is not required to do anything. It is just required to attach to the lifeline, and the system detects the fact that he has attached to the lifeline. If he attaches to the lifeline, the system detects it. If he signs a logbook and then he does not attach to the lifeline, the system can tell you this thing. But the worker is not required to know about all of these kind of stuffs. Of course, I'm just sharing with you what technologies can do, but not requiring that a worker can be.
Can you foresee the time that all this information gathered on what the worker has done and has not done will be transmitted back to a robot that will be walking along with the worker, and if the worker does something wrong, the robot gives him a kick?
No, maybe the robot helps him in rescuing. Maybe not today, maybe in 20 years, but I think it's.
Thank you.
Thank you. Regarding the time, if there are some more detailed questions, I think you will be available in the break. Nevertheless, don't forget Hall 6 and Genesi company, and then maybe it's good to see it in life.
Yes, it's a different thing to see it in life.
Yeah. Thank you so much. We have a break, next 10 minutes. Thank you so much.